In this session, we'll be discussing hydraulic hose failure modes and what we can do to reduce the incidence of hydraulic hose failure. Hydraulic hose inspections and maintenance are vital for equipment reliability and personal safety, with safety being everyone's prime concern and responsibility. The consequences of a hydraulic hose failure can include the following: personal injury, damage to the environment, damage or loss of plant and equipment, negative effect on machine reliability and availability, increased cost for maintenance and production, negative impact to business reputation. The course instructor will now refer to document New South Wales MDG 41 to discuss cases of fatal incidents related to uncontrolled equipment movement, uncontrolled release of energy, contact with moving or rotating plant and fire. The cases discussed were sourced from MDG 41, fatal incidents from fluid-powered systems. Oil spills in the environment can be disastrous, not only disastrous to the plant and animal, but to the local community and to the company. Oil leaks and environmental damage can destroy a company's good reputation. Fire. Fires can start from hydraulic leaks that a human eye can barely see. As seen here, the hydraulic hose has a pinhole leak and is leaking onto a hot engine, resulting in a plant fire. There is a significant hazard not only to personal safety, but to the entire business. The hazard can be easily reduced by the inclusion of hydraulic hose diffusion abrasion sleeving. This time, the hose is seen fitted with a DAS or diffusion abrasion sleeve containing the leaking fluid, in turn reducing the likelihood of a fire occurring. Machine reliability and availability. Does anyone know how much income is lost due to a machine being out of service? Let's assume a scenario. A machine is out of service for 2.5 hours. This machine could typically generate an income of $8,000 per shift. The potential cost of a machine being out of service due to unplanned replacement could look like the following: replacement hose, $500, equipment downtime, $1,000 per hour, so 2.5 hours is $2,500. Oil replacement, $250. Equipment cleaning, $200. Add labour and other incidental costs. So, as a minimum, we could expect the breakdown to cost over $3,500. Obviously, the breakdown of a larger piece of equipment could have huge cost ramifications. The projected service life in Scene A is 14,000 hours with the correct hose routing installation. The hose in Shop B's service life is halved at 7,000 hours due to incorrect installation. Lastly, the impact to business reputation can be many things, such as employee fluid injection injury, oil spills to the environment, machine damage, poor machine reliability, company to cut staff, business closes. All of this can be avoided with correct hydraulic hose inspection and installation practices. Accurate hose management is another tool that may be utilised in reducing hose failures and the associated consequences. Referring to Mining Design Guideline MDG 41, Fluid Power Safety Systems at Mines 7.6.2, hose failure modes. Typically, hose assemblies are discarded by either of the following two mechanisms. A. Inspection and assessment to discard reasons included: excessive mechanical damage such as abrasion, cuts and crushing, corrosion of both fittings and hose wire reinforcement, degradation age, chemical, cracking, overheating and fatigue. B. Catastrophic in-service failures, leakage bursts, hose to hose end separation and pinholes. Let's take time for a group question. Do we know what fluid injection is? And do we know what the injury could look like? A stream of pressurized fluid escaping that penetrates the skin and enters the human body. The injection of hydraulic fluid may cause severe tissue damage, loss of limb, and even death. The injury itself may initially look benign. The point of entry may even look very small and may not bleed. Initially, the patient may not complain of any pain, but may have a feeling of numbness. The affected body part will progressively become irritated, with the patient complaining of a throbbing pain. Due to the initial benign symptoms, these injuries are often complicated by a delay to seek medical assistance, often several hours. Without adequate and timely treatment, there is a high rate of amputation. How do we look for a pinhole hose leak? Never run your hands along the hose, even if you are wearing gloves. Your gloves will not protect you. To locate the leak, pass a piece of cardboard over the area or use a mirror where you suspect the leak may be. Always use extreme caution. The Mines Hose Management Plan should aim for the in-service inspection and assessment to discard the hose prior to a catastrophic in-service failure occurring. Let's discuss the hose assembly. A hose assembly is defined as a flexible hose and its hose ends attached. The hose end is defined as the hose coupling or hose fitting that is attached to each end of a single piece of hose. Hose ends should be properly matched to the hose based on proven type test results. Matched means that the hose dimensions and tolerances are compatible with the dimensions and tolerance of the fittings to ensure that the joint meets the impulse and burst tests for the hose assembly. Important note: Pertex matched hose assemblies are designed, manufactured and routinely tested to ensure compatibility, meeting and exceeding quality and industry standards. There may be other items included as part of the hose assembly. This may include steel spring guard, diffusion abrasion sleeve, sometimes referred to as DAS, spiral safety guard, grip check, or braided steel wire stocking. For this discussion, we will concentrate on basic hydraulic hose assembly, the hose and hose ends. A typical hydraulic hose is made up of three components: the inner liner, reinforcing, and the outer cover. A failure of any three of these components can lead to spillage and downtime. The inner liner is designed to convey the fluid or material running through it and are manufactured from various materials, including various rubbers, thermoplastics, and specialty materials. The reinforcement layer, or layers, contains the pressure. Materials used in the manufacture of reinforcing layers includes polyester, high-strength synthetic cord, high-tensile steel wire. The first hose shown is constructed using braids of high-tensile steel wire. The second shown is constructed using spirals of high-tensile steel wire. Hoses with braided reinforcing are used where there is a steady system pressure, and hoses that spiral are used where more flexibility is required or where the hose is subjected to high-pressure pulsations. The various types of outer cover are designed to protect the reinforcement from abrasion, ozone and weathering. The covering may also have fire resistance and anti-static properties known as FRAS. The hose ends can be roughly grouped as to how the hose and hose ends are attached. This includes push-on, generally for lower pressures, field attachment, otherwise known as reusable fittings, and crimping or swaging. Referring to Mining Design Guideline MDG 41 Fluid Power Safety Systems at Mines, Section 1.5.10, Hose Service Life. The effective lifespan of the hose, whereby the hose meets the required factor of safety and the required likelihood of failure, is typically a maximum of 8 years. Another standard by manufacture of equipment used at mines states, in short, the lifespan of a crimped hose assembly in use is for a 6-year period. The storage of a hose assembly is for a period of 2 years. And the storage of a hose without fittings is 4 years. Looking at the image of this ley line, does anyone know when the hose was manufactured? The ley line indicates that this is a Pertec hose. Is SAE 100, R2AT is the standard hose, was manufactured to. 06 refers to the bore size. The size is 3/8 of an inch. The hose is rated at 4,786 psi or 330 bar, has MISHA approval, and has a production code of 3Q17. The 3Q indicates that the hose was manufactured in the third quarter of the year, and the 17 indicates that the hose was manufactured in the year 2017. Let us now discuss defect identification. How did the defect occur? What was the root cause? There are many defects to look out for when inspecting a hose. We will now discuss the main and most common of these defects. Impact or crashing. Even hoses fitted with the steel spring guards are not immune from mechanical damage. The internal structure of the hose has been significantly damaged. This hose would in all probability burst if put back into service. Abrasion. Hydraulic hoses are used in tough applications and conditions every day. Abrasion is caused by rubbing of the hose against another material or even another hose. Wire fatigue. In the initial stages, the wire damage will not be able to be seen. It can be seen from the image that the outer cover has deteriorated. The reinforcement wires show signs of mechanical damage and are broken. Look for signs of excessive rubbing or chafing of the hose against sharp corners, brackets, incorrect routing, or the wrong size clamps. Excessive pressure. It can be seen from the images that the outer cover and reinforcement wires have been ruptured in an outwards direction. In this instance, the hose, which was rated at 700 bar, burst at 1,586 bar. Tail creep. Leakage occurs between the ferrule and the hose. Important note, ultimately, the hose assembly may completely separate from the hose. A probable cause? The shell of the fitting was crimped too much or too little during assembly. Another potential cause of tail creep may be the result of mismatched components. Erosion. Hydraulic hose tube erosion often causes external leakage. Hose erosion is usually caused by a concentrated high-velocity stream of fluid or by small particles in the fluid. See how the high-velocity fluid starts to wear down the inner tube of the hose over time. Corrosion is generally caused by misapplication of the fitting not suitable for the environment. The outcomes resulting in rust or electrolysis causing the hose to come loose from the fitting and burst as the fitting corrodes. Incorrect hose composition with wire reinforcement. Used in acidic environments, fluid can permeate through the outer cover and cause corrosion on the wire reinforcing. Kinking. Kinking refers to twisted hose. This is often caused by over-tightening or incorrectly installing the hose. When the hose is twisted, it stretches on one side of the hose and compresses on the other side of the hose. This applies additional stresses, weakening the hose structure. Bubbling on the outer cover. Bubbling or blistering is caused by fluid incompatibility with the hose materials. The blisters may contain fluid or a grease-like substance, which may be a combination of the system's fluid and the plasticizers in the hose. Pinholes. Pinholes may be caused in several ways, any of which results in an almost invisible sized hole that disperses hydraulic fluid at a very high velocity, potentially leading to a serious injury requiring the amputation of the affected body part. Heat. Hose failure can occur from overheating the hose assembly. Overheating will cause the hose to become very stiff. The inner tube will harden and begin to crack and will break down or harden under high temperatures. In some cases, the cover may show signs of being dried out. Delamination and swelling is caused when the fluid is incompatible with the inner tube material and the inner tube may partially wash out. Fluid incompatibility occurs when the incorrect hose is installed for the application. Refer to the Pertec catalogues to find the correct hose for the application. Application failures. Looking at the two hoses on the screen, can the group decide which hose is the right length and why? Hoses should be designed to accommodate length changes from changing pressures. As the pressure increases, the hose will tend to shorten. Looking at the hose on screen, what is the negative effect on the hose assembly in this scene? The life expectancy of a high pressure hose is reduced by as much as 70% with a 5-degree twist, and a 7-degree twist can result in a 90% reduction in service life. How could the twist have occurred? And how could we prevent this from occurring? In most cases, only one spanner was used to tighten the fitting. As the fitting was being tightened, a twist was applied to the hose. To prevent a twist from occurring, best practice is the use of 2 spanners. One spanner used to tighten the fitting, with the second to counteract the twist. There are many ways in which a twist can be generated by 2 or multi-plane movement. Here is one scenario. In the initial position, the hose has no twist. As the left-hand attachment moves towards the right and downwards to the secondary position, a significant twist is forced into the hose. As the element reciprocates back and forth, the reinforcing layers will be adversely affected, allowing the medium to burst through the side wall of the hose. In addition, the generated twist is applying a rotational force to the threaded hose ends. This torque, sometimes referred to as the invisible hand, can effectively undo the fastened fitting. An easy method of eliminating this error is by the inclusion of a swivel. Here is another example of incorrect hose end selection. Again, the generated twist is applied a rotational force to the threaded hose ends. What can we do to solve the problem? In this instance, using a hose with straight hose ends is the best practice. Looking at the image, what do you think is the problem with this hose assembly, and what can you do to correct the problem? The hose length is too short. This is putting significant strain on the hose ends, and the bend radiuses in the hose are too small. The reinforcing layers will be adversely affected, allowing the medium to burst through the side of the hose. Replacing the hose with a longer hose would be best practice in this situation. Let us have a look at a common hose connection system often used on plant and mobile equipment. This is sometimes referred to as 4-bolt flange, with several standards and designs being supplied to the market. For comparison purposes, we've selected a range of 1.5-inch hose tails including Code 61, Code 62, Letourneau Komatsu and Supercat. These hose tails are generally rated between 3,000 and 6,000 psi. Looking at these images, it may be difficult to see the important differences at the flange. This selection of hose tails are both rated at 3,000 psi and consists of Code 61 and Komatsu hose tails. Looking at the Code 61 and Komatsu hose tails, the flanges appear to be nearly identical. The difference here being, the O-ring groove in the Code 61 is imperial, while the O-ring groove in the flange for the Komatsu hose tail is metric. So, while there is only a small difference in these flange sizes, the flange clamps and Code 61 and Komatsu are compatible with each other. Looking at the hose tail selection again, the first hose tails are rated at 3,000 psi. The next hose tail is rated at 5,000 psi and is known in the industry as the Letourneau. Looking at the Letourneau hose tail, again it appears that this hose tail is very similar in size to the Code 61 and Komatsu flanges, but in this instance, the head of the Letourneau flange is thicker by approximately 3 millimeters. So, while there is only a small difference in these flange sizes, the flange clamps for Code 61 and Komatsu are not compatible with the Letourneau. Pertec list within their catalogue the AZLT split clamps, which are to be used in conjunction with the Letourneau flange. Moving on to the last of our selection, both these hose tails are rated at 6,000 psi. These hose tails are known in the industry as Code 62 and Supercat. The flanges appear to be very similar. In fact, the flange diameter and O-ring groove are exactly the same. Generally, all supercap flanges have a thickness of 14.2 millimeters, whereas the Code 62 flange in this instance is thinner by approximately 1.5 millimeters. So again, while there is only a small difference in these two flange sizes, the flange clamps are not interchangeable. In short, many flanges may look identical, but that is not the case, and mixing components can lead to system failure, severe injury, or even death and destruction of property. Looking at the O-rings used in more detail, we have already learnt that some styles of flange utilise imperial O-rings while others utilise metric O-rings. Just by looking at these samples, it's nearly impossible to see which is metric and which is imperial. Pertec lists within their catalogue the KY series of O-ring, which are metric to suit the Komatsu flanges. The Y series are imperial and suit both Code 61 and Code 62 flanges. All these have a round cross-section manufactured from Buna N and have working temperature range of -34 degrees Celsius and 120 degrees Celsius. The YD series of O-rings are for genuine Caterpillar XT flanges only. These have a D cross-section. Also listed are the OKS series high performance seal. This seal has a specialised rectangular cross-section and can be used to replace the Y series O-ring for use in arduous areas. These are manufactured from a polyester polyurethane material having a working temperature range of -30 degrees Celsius to 100 degrees Celsius. If a split flange is installed incorrectly, the O-ring will fail, resulting in an oil leakage. The correct installation of the flange is as follows. Inspect all components for damage or contamination, particularly at the sealing faces. Install the correct O-ring in the flange groove, ensuring the O-ring is not twisted. Lubricate the bolt threads. Align the flange and the two clamp halves to the port. Install the 4 bolts, hand tightening evenly to seal the O-ring on the port face. Torque the 4 bolts, alternating in a diagonal pattern to about 80 to 85% of the final recommended torque. Finally, torque the 4 bolts, alternating in the same diagonal pattern to the final recommended torque. Hose segregation. The use of P-clamps are helpful for segregating hoses so that the outer cover and braids don't wear away. Another way to segregate hoses is with the swivel saddles or rotating clamp. These are great as they physically hold the items that you are trying to segregate off each other, and as per the name suggests, they swivel. So they work even if the hoses aren't in line with one another. Looking at this example, the problem here being that the hose is rubbing on a sharp corner. What will happen to the hose, and what can you do to improve the situation? The hose is going to suffer from abrasion. The outer covering and the reinforcing layers will be adversely affected, allowing the medium to burst through the side of the wall. One easy method to reduce the problem is with the use of a spiral guard. A better idea would be the use of hose clamps to keep the hose away from sharp corners and moving parts. The use of a straight connection is applying force on the hose. The hose bend is starting too close to the fitting. Do you know what the minimum straight distance is from the end of the ferrule before the hose starts bending? Always have a straight section of 1.5 times the hose diameter before the hose starts to bend. An alternative in this situation would be the use of a 90-degree fitting. In this situation, there is a hose passing over a hot manifold. We feel that this is wrong. Why is this wrong, and how can we correct this? The heat from the manifold is going to adversely affect the hose. The hose is going to lose its flexibility and it will burst. We could isolate the hose with the use of a shield. Additionally, we could also use a heat sleeve to protect the hose. Clamping the hose in place in this instance would also be best practice. Hose protection. There are many ways to protect a hose while it is in action. Bracketing can hold the hose secure in place to stop any unwanted movement. Spiral guard to colour code and add an extra plastic layer. DAS sleeve to protect against abrasion. A heat sleeve for protection against external flames and high temperatures. Using this range of protective devices on the applications that are suitable can prolong the life of the hose and are a method of prevention. These products are not a solution for a damaged hose, and it is not recommended to apply these products to a damaged hose. Hose storage. Storing a hose correctly can also prolong the life of the hose as well as keep it clear of contamination and remaining as new as possible. This can be achieved by the use of plugs, caps, heat seal caps, and bags. It is Pertec policy to attach a service tag to the hose. In Pertec's hose tracking system, the serial number is linked to the hose assembly's unique bill of materials. Related manufacturing information, test reports, and service schedules for inspection or replacement. In recent years, for easy identification regarding the age of the hose, coloured zip ties have been used with a different colour for each year. For more information on hose protection and storage products, visit pertec.com.au or feel free to contact your nearest Pertec centre for assistance.